Have you ever really truly stopped to wonder what's going on inside your phone or your laptop? I mean, way down at the most basic level. Today, we're going to pull back the curtain and crack open the secret language that powers our entire digital world. It's simpler and, frankly, more elegant than you might think. So, let's dive in. It all really boils down to this one question. How in the world can a machine that is, at its core, incredibly simple, with a vocabulary that's literally just on and off, be able to do everything it does? I mean, creating stunning art, connecting us across the planet, it seems like magic, right? But the answer, you'll see, is surprisingly logical. And this is where it gets really interesting. Just look at the contrast here. On one hand, you have us. Our languages are complex, they're messy, full of nuance, with tons of characters and an infinite way to combine them. But then you look at the computer's entire universe, and it's built on just two states, power on or power off. That's the whole shebang. And we represent those two states with just two little digits, a 1 and a 0. All right, so here's the game plan for this explainer. First, we'll get into that secret language. Then, we'll figure out how you can possibly count using only zeros and ones. After that, we'll look at a really clever shorthand that makes life easier for us humans. Then comes the fun part. We'll see how computers actually do math. And finally, we'll connect all those dots and see how these simple little pieces build, well, everything. Okay, first up, the computer's secret language. So why base 2? Why not base 10, like us? Well, the reason is purely physical. Deep inside your computer, you have billions of microscopic switches, and a switch can only be in one of two states, on or off. There's no in between. So a number system with only two digits isn't just a good idea, it's the only one that makes physical sense for the hardware. And that system, of course, is called the binary system. We're all used to our decimal system, right? Base 10. It gives us 10 digits to play with, 0 through 9. Well, binary is base 2. It only has two digits, 0 and 1. But here's the secret. The real magic isn't about the digits themselves, but where you put them. Which brings us to our next point. How do you actually count with just two numbers? And this image right here shows the key to the whole thing. It's all about place value. You know how with a number like 125, we just know it's 1 100, 2 10s, and 5 1s? Those are all powers of 10. Well, binary plays by the exact same rules, but it uses powers of 2. So a binary number like 1011 isn't 1011. Nope. It's 18, 04s, 12, and 11. You add them up, and you get the number 11. That's it. That's how you can represent any number you can think of. So what if we want to go the other way? How do we translate our numbers into the computer's language? It's actually a super simple process. You just take your number, say 25, and you keep dividing it by 2 over and over again. Every time you divide, you jot down the remainder. It's always going to be a 0 or a 1. You keep doing that until you hit 0, and then you just read those remainders you wrote down from the bottom to the top. It's a neat little trick to speak fluent computer. Now, as you can probably guess, binary numbers get really long really fast, and trying to read or worse, type out a giant string of ones and zeros is just a recipe for a massive headache. So, to keep their sanity, computer scientists came up with a couple of clever shorthands to make these long numbers much easier for us humans to deal with. So this table lays out the main players in the game. You've got binary, our base 2 system. There's our old friend decimal, base 10. And then you see the two shorthands. Octal, which is base 8, and hexadecimal, which is base 16. And you might notice something funny with hexadecimal. It ran out of numbers. So it does something brilliant. It just borrows the letters A through F to represent the values 10 through 15. Pretty clever, right? And here's the really cool part. The whole reason we use octal and hexadecimal is because they convert from binary so easily. Because 8 and 16 are both powers of 2, you don't have to do any complex math. You just group the binary digits or bits. To turn binary into octal, you bundle the bits in groups of 3. For hexadecimal, you bundle them in groups of 4. It's this awesome shortcut that programmers and engineers use constantly. Okay, this is the crucial part. So a computer can store numbers in binary. Big deal. How does it actually do anything with them? How does it calculate? Well, this is where the real power of this simple system shines through. It all comes down to just a handful of incredibly simple rules. Let's start with adding. Seriously, forget everything you learned in elementary school about carrying the 1 and all that. In binary, there are only 4 things that can ever happen. 0 plus 0 is 0. 1 plus 0 is 1. The only one you have to think about is the last one, 1 plus 1. The answer isn't 2. Remember, there's no 2-digit. So the answer is 0, and you carry a 1 over to the next column. That's it. That's the entire instruction manual. Okay, let's put this to the test with an example we all know by heart, 5 plus 5. We know the answer is 10. So in binary, the number 5 is written as 0101. That means our problem is now 0101 plus 0101. Let's see what happens. So we work from right to left just like we always do. First column on the right, 1 plus 1. Okay, that's our special rule. The answer is 0, and we carry a 1. Next column, we have 0 plus 0 plus that 1 we carried over. That gives us 1. Third column, it's 1 plus 1 again. So that's 0, and we carry the 1. And in the very last column, it's 0 plus our carry, which is 1. And there's our final answer, 10, 10. But what is that in our numbers? Well, let's translate it back. We have 1, 8, 0 4s, 1 2s, and 0 1s. So 8 plus 2 is 10. It worked! The computer got the right answer just by following those 4 simple rules. So what about subtraction? It's pretty much the same deal. Again, just 4 rules to remember. And just like with addition, there's only one tricky case to watch out for: 0 minus 1. You can't do it directly. So just like when we were kids, you have to borrow from the column next to it. Okay, let's test it out. A nice, simple problem. 5 minus 2. We know the answer should be 3. So in binary, that's 0101 minus 0010. All right, here we go. From the right, first column, 1 minus 0 is 1. No problem. Now the second column, and there it is, 0 minus 1. We can't do that. So we look to the column on the left and we borrow from it. That 1 becomes a 0, and our 0 basically becomes a 2. So 2 minus 1 is 1. Now we move on. The third column is now 0 minus 0, which is 0. And the last one, 0 minus 0, is 0. So our final answer is 0011. And if we convert that back to our decimal system, well, we've got 1, 2, and 1, 1. That equals 3. And what do you know? 5 minus 2 is 3. The logic is rock solid. So how do we get from adding 5 plus 5 to playing a video game or editing a movie? It seems like a massive leap, right? But the truth is, these incredibly simple operations are the absolute rock-bottom foundation for everything a computer does. Everything. You might be thinking, okay, addition and subtraction are easy, but what about multiplication or division? Well, as this quote from the source material explains, multiplication is actually just a really fast series of the additions we just did, combined with a simple trick of just shifting the bits left or right. Every complex task you can imagine gets broken down into millions or billions of these tiny, simple steps, all happening in the blink of an eye. So let's just recap the big ideas here. First, computers speak binary because their guts are made of simple on-off switches. Second, absolutely any piece of data, a number, a letter, the color of a pixel, it can all be represented by a string of 1s and 0s. Third, we invented shorthands like hexadecimal so we humans don't go crazy trying to read that code. And most importantly, every amazing, complex thing your computer does is built on a foundation of math that is, frankly, ridiculously simple. And that kind of leaves us with a final thought to chew on. We've just seen how the most mind-blowingly complex software in the world is built from the simplest possible set of rules. It really makes you wonder, doesn't it? What other huge, seemingly impossible problems in our own lives could we solve if we just found a way to break them down to their most basic, fundamental parts?